Okay, the exam. Wednesday. Same procedure as previous exams with the location and times. You can come at, what is it for this class? 1:30 or 2 to that library, the room in the library, same room. Hour and a half exam. What else? So a calculator. You may have a basic scientific calculator. Normally they have a one-line display. No graphing calculators allowed. No graphing calculators allowed. Only basic scientific calculator. So it's the kind that might cost $6 or $7. Okay, so you can borrow one of those, or probably most of you have one, or buy one. It's like there's basic, no graphing calculators allowed. It covers sequences up through Taylor and Maclaurin series. So it's this component we've been working on. Any questions about the exam? Calculator, location. Okay, so we were doing, am I recording? I think I am. Okay, so we were doing a cosine x, and I think we came up with this. Did we come up with this for cosine x? 1 minus x squared over 2 factorial. Did we actually change the index and get this? We let j be 0, 1, 2, 3 on the non-zero term, so we like re-indexed it. Or when we first did it, we got zeros in between each. Like a 0 for the x, and then 0 for the x cubed, and then 0 for the x to the 5th. Then we re-indexed it and got this. Oh, am I back? Yes. There we go. All right. Okay, got it. We are here. Okay, so what I want you to do is, so this was the Maclaurin polynomials. I want you to sketch, let's zoom in. I want you to sketch the first 3 Maclaurin polynomials. Now this is not with you're not doing any computation, you're not calculating any numbers, you're not using any technology, you're just by your understanding of Maclaurin polynomials, sketching them. So like I could have asked you to do this before we even started building the series, okay? So without the series, can you sketch the first 3 Maclaurin polynomials? See if you can do it. This is a good kind of test question, good conceptual test question. Can you sketch the first 3 Maclaurin polynomials for cosine x? You can consult those around you if you need help. I'm getting on my list. I have it. Question?
Do you want the first non-zero ones or just the first?
I want 3 different Taylor polynomials.
Thank you.
Yeah. Okay. Okay, how about Jessica Leifel? Where's Jessica? Jessica here? Jessica? No? How about Micah, where's Micah Band? Micah, how'd it go? What was the first one you came up with?
For the first one, it's just constant line.
Yeah?
At y equals 1.
He wants a constant line at y equals 1. Okay? And so then what would so that's like the 0th degree Taylor polynomial. So what about the 1st degree Taylor polynomial? Like the one that would be a linear approximation. So what would... Okay? So yeah, it gets the slope right. And what would that be? What line gets the slope correct as well as the function value correct? Yeah.
Is it 1 plus the x squared over 2x?
So is that linear? It's x squared. So that would be, actually that would be the next one, right? So what about the linear? Nick knows. Anybody else? Yeah. What's that? Yeah, so it actually ends up, that constant line is also the linear approximation because the slope is 0. So that's why the terms got skipped. So that's the 0th degree Taylor or Maclaurin polynomial, but it's also the 1st degree. It's also the linear because your slope is 0 at y equals 0. So it does both. See that? So it not only gets the function value right, but it gets the first derivative right. Okay, so then what about the next one? So then Deanna, that would be the next one. What would that be?
No, 1 plus x squared over 2x.
Right. Is it plus?
Oh,
Yeah. I think that just multiplied it. Okay, so, and what does that look like? What if you were just sketching that? What would that look like? Opens which way? Down, right? So it's going to start matching the shape of the graph at x equals 1. So that would open downward. Okay, what about the cubic approximation? So what about, so this is the quadratic approximation. What about the cubic approximation? Yeah, Dylan. Yeah, right. So by the same reason as before. So this will get the 3rd derivative right. Because if we add the next term, then we're talking about the 4th degree. So it happens that all the even degree polynomials, they also get the next odd derivative right. So they're actually the next odd degree polynomial as well. So this will not only get the 1st and 2nd derivative right, it also gets the 3rd derivative right because of the nature of cosine at 0. So what will the 4th degree look like? So now this is the 4th degree Taylor polynomial. What will that look like for cosine? Mark, can you describe it? Or are you just kind of drawing it with your finger there?
It's going to be like, I can't, I don't know how to describe it.
Yeah, so it'll still open downward at 0, but then what will it do? Yeah, then it'll loop back up again, right? So that's our 4th degree Maclaurin polynomial for cosine x, and it's also the 5th degree. Just by the same reasoning as before, this also gets the 5th derivative correct. So did we find out for what values cosine x converges? So we found that series. Here's the series for cosine x. How would we find out for what x values it converges? Ratio test, right? This is a power series, and we use the ratio test to figure out for what values it converges. So I'm just going to tell you, you can check it later on your own to confirm. But if you were to do the ratio test, you would get that it converges for all real numbers. So you should do that on your own. It's another, doing lots of those problems. Confirm that it converges for all real numbers. Meaning that, what does that mean? That means if we were to add up all infinitely many terms of this series, what would we get? If we were to able to add up all, just go on adding, make this an infinite polynomial, add all the terms forever, what would we get? Cosine x. For what values of x? All of them, right? It'll reproduce cosine x perfectly for all values of x. And we see that happening, right? As we keep adding more and more terms of the polynomials, what happens to the polynomials then? What's going on? How does it convert? What's happening that it's reproducing cosine x? How does it do it? Is it all correct but too high, and then it's slowly coming down and converging by coming down onto cosine x? Does it get it right at the ends and then work its way to the middle? How does it get it right as we add more terms? Right, from the inside out, right? So this is going to be the 12th degree polynomial, and so what do we see? No, something went. What did I do? Let's try that again. All right, we'll add 3 more terms. There we go. Let's try that. That's better. So here's what the 10th degree Taylor polynomial. So here it gets it pretty close to correct all the way from -4 to 4. Whereas this earlier ones got it correct or close for a smaller range. All right, then we'll just go ahead and add up to 18 here. So here's the 18th degree Maclaurin polynomial. So see what's happening? So we're centered at 0. So for each Taylor polynomial of higher and higher degree, it matches the curve for a larger and larger interval around 0. Kind of works its way out. And if we just kept going infinitely, if we were somehow able to add all infinitely many terms, we'd get cosine x exactly everywhere. Okay, so that's what's going on here. Any questions? All right, so why don't you try? You can work on the Taylor, go back to Taylor polynomial for ln of 2x, centered at x equals 3. All right, so do you agree with my derivatives? Check out the derivatives there, see if you agree. Yes? A few nods. Okay, so writing it out this way is really helpful for then trying to figure out what the term is. So this is like we're looking at a sequence now. We're trying to figure out what the nth term is, because that will help us now write the Taylor series. Because we'll have the derivative, right? And we can have that. We'll do that at 3, and then we'll need the n factorial, and then we'll need the x minus 3 to the n, and then we have it. So then we have the general term when we put all that together. But this table is really just helping us get this right here, right? That's what this is helping us get, the table. The derivatives at 3, and then a general formula for the derivative at 3. For the nth derivative at 3. Okay, so what do we see there for building a formula here? So it looks like we've got, what pattern is going on here? These are factorials, right? So everyone think, don't just yell it out. What factorial is for the nth derivative? What factorial do you have? Looking at the factorial for the nth which factorial do you have for the nth derivative? N plus 1? So for the 7th derivative, we have 6 factorial. For the 6th derivative, we have 5 factorial. Therefore, n minus 1, right? It's the n minus 1 derivative, or factorial, sorry. And then what, divided by x to the what? So what power do we have in the denominator? N, right? We have the nth power in the denominator. Anything else? Times negative 1? Alternates, right? So we have a negative 1, but only on the even derivatives, right? On the 2nd, 4th, 6th, etc. So how do we get that to work? Negative 1 to the? Yeah, so we're going to, so if we need it to be negative on the evens, we're going to need power n minus 1. Because if you do n makes the even powers positive, and n minus 1 makes the odd powers positive, so we need n minus 1 to get the even powers negative. So then now what's the general term at x equals 3? It'll be the same thing as this, except what's the only difference? So now looking at, say, the nth derivative taken at 3, what will you do to this to get the nth derivative taken at 3? Plug in 3 for x. That's only in the denominator here. So then in the general term for the nth derivative at 3, we'll get, this will be 3 to the n. Okay, so that's what this is, what I circled in red. That's the nth degree derivative taken at 3. And then for Taylor series, for the coefficient, we also need n factorial and x minus 3 to the n. So can you write it out? So this is natural log of 2x equals, oh, but notice what's happening here, right? What about this first term? ln of 6, is that what you get when you plug 0 into this? No, so what do we have to do? We have to throw it out here separately. We're going to have that ln of 6 separately, and then start at 1, because now the pattern starts when n equals 1. Do you see that? Does that make sense? The function is natural log, and then all these other functions are 1 over x to a power. So those follow a pattern, but this doesn't fit that pattern, so we need to have that initial term. Okay, so our nth derivative at 3 was negative 1 to the n minus 1 times n minus 1 factorial over x to the n, but now we're evaluating at 3, right? So over 3 to the n. So that whole thing is just my derivative, what I circled in red. So what I've written so far is only what I circled in red, right? It's our formula for the nth derivative. So what else is there? Yep, we're going to need the n factorial. It's part of the coefficient. And then also, okay, so do you follow it? So I'll circle this in red also here. So what I've circled in red is what we found by the table, just the nth derivative. But the coefficient in the Taylor series is the nth derivative divided by n factorial. We derived that 2 classes ago. We figured that out. So that's why we get the red thing over the n factorial times x minus 3 to the n. That makes the Taylor series. Okay, now that being said, is there anything we can do here? Looking at this expression, can we clean it up any? What's that?
Is the n minus 1 on top because the factorial?
Is that how it works? N minus 1 factorial over n factorial is n minus 1?
The n on the bottom
Hold on a sec.
you'd have n minus 1 multiplied by n factorial, and underneath you'd have n factorial, so you can cancel out the two n factorials, and you'd have n minus 1 on top.
You got the right idea, but you're kind of backwards there. What is n? N factorial equals n times
Is it n
n
minus
minus 1 times
times n minus 2?
n minus 2 all the way down to 1, right? So this is what we have in the denominator. And what's n minus 1 factorial?
N, oh, okay.
You see it?
Yeah, I see it now.
Yeah, so you remember kind of what
I was
happens.
thinking n plus 1 rather than
Right, right. If you had n plus 1 factorial on the top, then it would leave an n plus 1. But this does not do the same thing, right? What does this do?
So then it would be n in the denominator.
Just n in the denominator, right? So this thing right here is just all it amounts to is a single n in the denominator. Do you see that? So we've shown that here. So we'll have times x minus 3 to the n all over 3 to the n and n factorial. Oh, n, sorry, n. Because all these go away, leaving n in the denominator. So I think that's it. So for what values of x does this series, right? So what is this? This is a series, and what's the general idea of this? What kind of thing is it generally? Okay, it's a sum, good. And what kind of sum is it? It's like what? It's a sum, it's an infinite sum. It's like, what kind of function? Polynomial, right? Power series are like polynomials, right? Okay, and so if I was able to add all infinitely many of those terms, what would I get? ln of 2x. What if I wanted just to get something decent? I don't want to get it. I don't want to spend the rest of my life and forever after that adding up all these terms because it would take forever. So I just want to get a decent approximation for ln of 2x. What would I do? I know Neil and Nick know. I want to get a decent approximation for ln of 2x. I have the Taylor series, which gives it to me exactly for all infinitely many terms. Super important principle we've been working on the last month. Got 4 or 5 hands. Logan, do you know? Right. Don't take all the terms. What do we call that? A partial sum, right? If you take a partial sum and to stop, then you get an approximation. And if you want a better approximation, you do what? Take a higher power partial sum. Take more terms, right? Every partial sum is an approximation, like I've been showing you with the graphs. And then the higher the power, the better the approximation. Okay? Super important principle that partial sums give us approximations to the series. The longer the sum, the better approximation of the series it is. Okay, so now the next question is, does this give us ln of 2x for all x values? Yes or no? How do we know for sure? Some are saying no, some are saying yes. How do we find out for sure? Ratio test. Gotta do the ratio test. Go. Ratio test. So another question is, do you agree with that? You get it this far? Did you make it this far? So now the question is what, so as n, the limit as n gets big, what happens when n gets big? What do we have? Okay, good. Let's see. What do we have when n gets big? Dylan, do you know?
Me?
No, Dylan in the back. So really all we have to look at is this. What happens to n when n gets large? 0? Well, I got an n on top too. N over n plus 1 goes to, oh, please know this. 1, right? 1. Sequence, n over n plus 1 would go to 1 because we have the same degree. Same degree, we look at the ratio coefficients. And so as that thing goes to 1, our limit is x minus 3 over 3. Ooh, I'm running out of space here. So, this over here. So then what do? If x minus, the absolute value of x minus 3 over 3 has to be what? Less than 1, right? Ratio test. Ratio test says, look at the multipliers, right? Look at the sequence of the next term, the ratio of the next term to the current term. That's what we did here. A of n plus 1 divided by a of n. That's the ratio of the next term over the current term. That's the multiplier to get to the next term. If that multiplier converges to a number less than 1, what do you have? You have like a sequence that's like becoming geometric and converging, a geometric sequence that converges. So that means x minus 3 over 3 has to be greater than 1 and less than negative 1, which means x minus 3 has to be between 3 and negative 3. So between, they're saying up here 0 and 6. Agree with that? Last. So we're going to add 3 as the last step. Add 3 to all sides. You get between 0 and 6. What about at 0 and at 6? Got to check it, right? We got to check it. So sometimes you'll get both endpoints, it will converge at both endpoints, neither endpoint, sometimes it's one or the other. So at 0, what do? We take 0 and we put it back into our original sequence. So we're going to put 0 in there. And can we work this out on the fly here? We're going to put 0 in. I'm going to get negative 3 to the n over 3 to the n. Just like negative 1 to the n. And then I have another negative 1 to the n minus 1. So that all kind of goes away, right? So we got negative 3 to the n over 3 to the n times negative 1 to the n minus 1. So I think that whole thing becomes negative 1. So when x equals 0, does that thing converge or not? It's basically, I basically get the series negative 1 over n. Converge or not? That's the opposite of the harmonic series. Diverges. So we're going to have strictly less than 0. Then I'm going to put x equals 6 in there. What do I get when I put x equals 6 in? 3 to the n over 3 to the n goes away. I get the alternating harmonic series. Do you see it? Converge or diverge? That converges. So I got negative 1 to the n minus 1 over n converges. So here we see that it converges on the right, but not on the left. So this Taylor series only works, it only reproduces natural log of x between 0 and 6. First of all, what about natural log? Where is natural log defined? Only positive numbers. So this agrees with that, right? It wouldn't make sense if we got x equal to 0 or less than 0 because that's not, the natural log isn't defined for those values. But then this is showing, so for anything greater than 6, this series will not reproduce natural log of 2x. It's only going to reproduce the function between 0 and 6. Questions on any of the math to get that result? So we got the Taylor series, and we got the interval of convergence for what values of x that Taylor series actually works. Anybody have a question? Okay, we're going to look at the graph, and I'm going to have you, so while I'm getting that up, I'll just sketch the graph, and the graph of natural log of x looks like what? Looks like this. And we're centering at 3. So while I'm getting the GC file ready, I want you to sketch the first 3 Taylor polynomials for natural log of 2x centered at x equals 3. That's what we found. So sketch like you would have done before we did any of this work. Okay, so it's all based on your understanding of the Taylor polynomials and what they do. So you're not doing any computations, no technology. You're just sketching the first 3 Taylor polynomials for that graph. Okay. The first Taylor polynomial. Who's up? Hunter. What's Hunter? Hunter here? The first, is that you? Oh, sorry. Hudson, Hunter Hudson. Who's that? That's you, okay, cool. So what's the first, can you tell me what the first Taylor polynomial is? Okay, so like the 0th degree. I guess, so you're thinking the first degree? Yes, 0th degree. Horizontal line at x equals 3. So at the function value, right? At the function value. So for your first one, you should have drawn that. What does it get right? It only gets the function value right. Okay, next one. So now the first degree Taylor polynomial, which is the sum of the first. So that's just the ln of 6, right? That's the one that's outside of the summation. So now we have ln of 6 plus the linear term, which gives us the first degree Taylor polynomial. What is that? Lee, what did you draw for the next one?
Kind of a slope going through 3, like it has a little bit more accuracy, but still not much.
What's the next thing that's accurate about it?
The area around 3 is a little bit more accurate.
Okay, but that actually that next Taylor polynomial is exactly right in what respect? So this one just got the function value right. The next one gets the function value and the slope, the first derivative, right? So there's that. That's the linear or the first degree Taylor polynomial. That's the second graph you should have drawn, and then the third one will be Chance. Opening which way?
Down.
Opening down, right? It's going to have the same concavity as the graph. So that's the third graph you should have drawn. A parabola. So that gets the first 2 derivatives correct. And then what do we expect as I take higher and higher derivatives? How's that red graph going to match the blue one? Where is it going to match the blue one? From 3 outward. So then will it eventually get the whole graph? Nope, only what? Until 6, right? So watch what happens as I take one more term each time, right? These are partial sums of the Taylor series, so they're Taylor polynomials. This is the 10th degree, 11th, 12th, 13th. Look what's happening here too. Look what's happening by x equals 0. Watch what happens by x equals 0. Do you see that that's converging as well? And we know this is going to converge for all x greater than 0, so that red graph will eventually get the blue graph, get the natural log. But here, greater than 6, it's just going to keep flipping up and down, but will converge at 6. We showed that at 6 it will converge. So right there, at x equals 6, it will converge. But as soon as x is greater than 6, it's just going to, the Taylor polynomial is going to go to infinity. But to get that value right at x equals 6, you need all infinitely many terms. You're going to need all infinitely many terms, and then it'll finally get x equals 6 right. And that's true for any value except 3. Right now at 3, it's getting the function value right and 20 derivatives right. But as soon as you move away from 3, it's approximating the function better and better and better. You need all infinitely many terms to get the function exactly right in the interval of convergence. And what was it? It was from 0, not including 0, to 6, including 6. Any questions? Canvas quiz. Canvas quiz. One question.